All right, so I have here an energy diagram. It doesn't represent anything in particular. It's not just gravitational potential energy because it's not a straight line. It's not just elastic or spring potential energy because it's not a perfect parabola. But we don't need to worry about that. One thing we do keep in mind, though, when we're looking at an energy diagram like this, where we are defining the total energy. So TE, they're representing as total energy. This energy being constant, we're saying that all of the potential energy and kinetic energy in the system at one moment in time is still there, finally, at another moment in time. Turning point, they have that labeled here. If you remember from the previous energy diagram videos, where the potential energy line, this curvy one, so PE, capital U, our potential energy, where those intersect, this is the location. All the energy is potential, none is kinetic. And so whatever the system represents, the object is in the process of heading back in the opposite direction. Now again, the potential energy portion of the graph that goes above the total energy is just theoretical. You could technically have more potential energy, but for the situation in which this graph represents, those potential energy lines continuing above total energy don't matter. So we've already talked, we know that the distance from the horizontal axis up to any point represents the potential energy at that moment. And then if we continue and measure the rest of the way, that represents the kinetic energy. So the particle starting from rest here on the left, we let go, it's moving downwards. So as it continues down this slope, its potential energy, U, is getting smaller, which means K, its kinetic energy, is getting bigger. At this location right here, it's like rolling a marble through a bowl. The bottom of the bowl, this kinetic energy is the biggest it's been in this section, but now as we continue to the right, the potential energy is increasing, which means kinetic energy is decreasing. So down here at the bottom, this is essentially explaining what we would be seeing. This particle is going to speed up, but as soon as it reaches that bottom dip, it's going to start to slow down. That is true until it reaches this peak, because now the potential energy is going to decrease again, meaning the particle will speed up. This lowest point is when the kinetic energy is biggest. That's why they labeled this the point of maximum speed. And then as the particle continues to the right, it would slow down until it gets to this turning point. But it won't stop there. We would see the particle head back the opposite direction, and we would see it speed up, and then slow down, and then speed up, and slow down, until it got to that maximum point, and then it would go to the right again. So we would see just this continuous motion of speeding up and slowing down. You can really almost think of this as a roller coaster track if you wanted, or a marble track. You put a marble on the track, it goes down the track, back up and down, back up, and we're assuming absolutely no friction or drag because these diagrams don't apply if we're creating other types of energy. So those would drag and friction would create thermal energy. So we're assuming a very perfectly ideal situation, which of course would not be representative here. The total energy in any given system depends on the maximum height if we're talking gravity. It depends upon the maximum stretch or compression of a spring if we're talking a spring. So this total energy line is specific to a given problem. Now, if you remember in the last video, I mentioned how we can figure out force if we look at the slope of the tangent line, meaning the line tangent to the potential energy. So at any point on this motion, we could look at a slope of a tangent line, and that would relate back to the force. But notice right here, and right here, 1, 2, 3, we have 3 locations where the slope is 0. What that means is that the net force is 0 at that moment. So at that moment, there would be no acceleration. That means if the total energy line was down here instead, where it intersected this slope at the peak at point 2, if I placed, let's go back to pretending this is just a track for marbles. If I placed a marble exactly at that location, not letting it roll down the hill, just physically take a marble and set it right there. If I am really good at placing it just right, with this net force of 0, the marble would stay there. All of that energy would be potential, but if there's no net force, it would stay stationary. If you remember, we called this an equilibrium location. An object at rest and staying at rest, not going anywhere, we would call that equilibrium. Now, of course, getting that marble perfectly stabilized at that location is a challenge, because if I just accidentally set it even just the tiniest bit to either side, where the slope of the tangent line is just barely not 0, then there's a force, and that force is going to cause an acceleration. That marble will roll away. We call this a location of unstable equilibrium, meaning the object, whatever it may be, a marble on the top of a little peak, if we place it just right, we can get it to stay there, but even the tiniest bump would make it move away. So the term for that is unstable equilibrium. But if we come back to our graph and think about point 1, if the total energy was just right there, let me erase some of my picture. If the total energy was this new line that I've drawn, and I placed a marble right there, it's all potential energy. Again, all of that energy is potential. The net force is 0 because the slope is 0. This is a location of equilibrium again. But this situation is different. If we imagine I was a little bit off and I accidentally or purposefully put the marble just a little bit to the side instead of perfectly in the bottom, because the slope there is not 0, there would be a force, the force would cause an acceleration. Hopefully, we recognize that marble would roll towards the bottom. What we would end up seeing is the marble rolling back and forth in the bottom. Eventually, if there is the friction, eventually the marble would come to rest and just sit there again. We call this a location of stable equilibrium, meaning even if this little marble is given a little more energy, it's still going to roll back to its original location to stay there. Another good example of stable equilibrium would be if I have a mass on a spring. If I pull this mass downwards and let it go, I know it's going to oscillate up, but back down, up and down forever if there was no friction, which of course realistically there's going to be some thermal energy generated. As time goes on, all that will happen is this mass spring system will eventually come to rest in its equilibrium position. We call this stable equilibrium. If we add energy to a system in stable equilibrium, it will oscillate until eventually, assuming there's thermal energy generated, eventually it will come to rest back at its equilibrium. So unstable means it doesn't come back. Stable means it would come back. So these are the main pieces that we want to understand. The potential energy is changing with time and position. If we measure from the horizontal axis to any point is potential, above is kinetic. The total energy is determined by the system itself, the maximum height a ball would reach, the maximum stretch or compression of a spring. If we are given a graph, we would have to be given enough information to know what the total energy is in order to answer questions about the graph. The other concepts are the turning point and then this idea of equilibrium, where the slope is zero, because we can always relate the force on the object to the slope of the tangent line.